have interview and Q&A session with Cindy Sridharan. And my guess that Michael Druzhinin will help me with this. And actually, who is Michael Druzhinin? Have you heard about him? He's actually working in Amazon Web Services, and probably you heard him in a few podcasts, and even you might seen him at several conferences. So he's actually worked in for about maybe 13 years in IT, and he was actually a Java developer and architecture in different companies. And right now, as I said, he is a software development manager in Amazon. Welcome to the broadcast, Michael.
Hey, Seva.
Hello, how are you? How are you doing?
Hey, folks. I'm quite good. How are you doing, folks, here?
It's
Uh,
quite dark compared to yours environment.
it's quite wide. And yeah,
It is.
I have a bigger heart to introduce Cindy and have a Q&A session today with her. Cindy is a distributed system engineer in San Francisco, and moreover, she's author of a book of distributed system observability, and more books is coming up. Today we'll have Q&A, so feel free to ask as many questions as you want in Telegram chat, and we'll try to cover all of them in 1 hour. So just don't hesitate. And Cindy.
Hello.
Hey, glad to see you.
Hey,
Good to see you too.
Cindy. Great to see you here, and great to have you on Hydra conference. It's honestly a big honor for us. And maybe you can introduce yourself for our audience and give more deep and broad information about yourselves.
Sure. So I am really excited to be a part of Hydra. I think this is one of the absolute very best distributed systems conferences in the whole world. It definitely is way better than, just going by the previous year's talks. It's just head and shoulders above a lot of conferences that I attend here in the United States. So, just thank you to all of you guys for putting up such a phenomenal conference. This is amazing. And I was really looking forward to actually coming to Russia because I've never been there before. So I was really looking forward to that. But thanks to COVID, that didn't happen this year. But hopefully maybe next year I'll be able to visit Russia in the summer, because I've heard it's really beautiful. So a little bit about myself. I'm a distributed systems engineer. I am based out of San Francisco, and for almost the entirety of my career, I've been building large-scale systems. And for the most part, I worked at small startups in the San Francisco Bay Area, and I was also very lucky because I got the opportunity to work at startups that were really dealing with problems of scale and were really dealing with large-scale distributed systems problems, which not a lot of startups deal with. And that is totally fine, because a lot of startups are all about, just building a great product. But I was lucky because I ended up working at places that had real, true distributed systems problems. So almost everything that I've learned about building large-scale systems has come from, real-world experience. And 2 years ago, I published a very small book called Distributed Systems Observability. That was when observability was still, a fairly new idea. And most of the content of the book was about how it differed from monitoring and, what are the key aspects of observability and how it impacts building large-scale systems, especially more modern cloud-native systems. It was a very small book. It was more like a report. And I'm actually pleased to announce that there are way better books on the topic of monitoring and observability these days than it existed 2 years ago when I wrote something. There's a new book on distributed tracing written by Jonathan Mace. This is a book from O'Reilly, and it's just been out for about a month or two. And the book is amazing because it is authored by a lot of people, both people from the industry as well as people doing cutting edge research in observability. And there's also another book coming up from Riley on the topic of observability. So if anyone wants to learn, more deeply about these topics, then I would recommend reading those books. But yeah, so, but I published probably what was the very first book on the topic of observability 2 years ago. And, I am also working on another book. I don't know if it will ever be published, if I'm ever going to be able to finish it. It's just so hard to find time. But hopefully, if someday it sees the light of the day, then that'll probably be my second book.
Oh, it's really cool. And just to start some warm-up about observability and distributed systems, what's let's say, the smallest and easiest topic for you when you start speaking about distributed system?
Oh man, are distributed systems easy? Can any topic be considered easy?
Just some
I mean,
starter.
I think every single, oh man, I don't know. Pick your own. We can talk about anything here.
Okay, I had one in mind about some health status of a system, and like what's mean for distributed system even to be healthy.
Well, the basic premise of distributed systems is that, they don't always exist in a state of complete healthiness, right? A lot of real world systems are never completely entirely up. They're in some form of, being, they're in some form of working in a degraded state, or, being in a completely non-optimal state at all times. And one of the most important aspects of distributed systems architectures is to build systems so that they can continue to exist and evolve in this state of almost constant unhealthiness, if you can call it that, which is a really weird way of thinking about it. But no system that I have worked on has, always been 100% up 100% of the time, which is again why people think that aiming for something like 100% availability in distributed systems is completely, it's almost completely unachievable, because you're never going to be able to hit those SLOs. So health as such is something, because when people think about health checks in distributed systems or health of a distributed system, we think about it in terms of binaries, which is like, it's either unhealthy or it's unhealthy. And it's not just, we as human beings or we as, distributed systems engineers who think about it that way. A lot of distributed systems have been built in that way, which sort of assume that, either the system itself or another system is either up or down, right? A very good example would be cluster schedulers. You have systems like Kubernetes and Mesos. A lot of these schedulers constantly health check the applications that they're running. And if the application is down, they, number one, they stop sending it traffic. Number two, they restart the application or restart the same application on a different node. So a lot of systems and a lot of operators are, the way we've been thinking about health is like, in the form of this binary, it's either up or down. And in my experience, that is, somewhat true, but a lot of the most interesting distributed systems failure modes and a lot of the most unexpected failures that I've seen in systems has come due to this folly of seeing systems as, systems health as like a binary entity, whereas health, in my opinion, is more of a spectrum. Your system, not just an entire system, but also like a single process on a single host. It's very common that, it's in the easiest scenario, it's the case that the system is completely crashed, right? A process is completely crashed. And that is easy because that is a very well-known, a very sort of like, there's no ambiguity there. It's just a very hard failure mode. And those kind of failure modes are very easy. But a lot of failure modes, which are kind of harder to reason about, are the ones where you don't really get, the complete failure of a system. But what you really have to deal with is a system that sort of like fluctuates, where the system's health fluctuates, right? It's sort of like down for a while and then it's kind of back up. A very good example would be like a single asynchronous RPC server that's just serving RPC requests. It could be that, the system is completely up. It's all of its health checks are passing, but the system is completely overloaded because, it just has been inundated with requests. There's just way too much work that it's been sent that it cannot do. So even if it's up in theory, that it's not completely crashed, its response times are slower. It's just doing too much work, and people are getting a, more degraded quality of response. And in that case, from the perspective of certain other systems like schedulers or even operators, that process is not completely down. It's still up. It's still answering health checks. It's still doing some work. But from the perspective of a user, that process is, it's not going to beat the SLOs. It's not going to meet the, response times that people expect, from that service. So, so this is just one example where, thinking of health as a binary entity is problematic because, there are, especially at, very high levels of concurrency or very high levels of load or during like very bursty or peak loads, it's very possible that a system can be up, but it's still sort of like working in a very degraded mode.
Yeah, it's totally makes sense. And how to live in this world where system is not fully healthy? And they definitely know that a lot of folks expect, okay, it's working and it's not working, but how to operate in a case when system consistently have some degraded experience? So what techniques can help to survive basically there, or maybe vice opposite direction to make sure that we improving this health and provide actually a response for customers instead of just say no, we're healthy, but we'll get back to you in next few days.
One of the, there are several techniques that work here, and it's more important to kind of like understand the root, or the proximate cause of this problem, rather, before we sort of like jump to solutions, before we jump to saying like, okay, what are the ways we can fix this? And one of the reasons why this happens, or one of the reasons why this is problematic, is because the process alone, or a single entity or a single node alone, knows just how much work it's able to do, or just like how overloaded it is. And in a lot of scenarios, like upstream services or services that send requests to this, this process that's sort of struggling, they have no idea that this process is down because, all that the health check says is that, it's up. So, that's one of the main problems is the lack of a feedback loop between, services and, their immediate downstreams. That a downstream to a given service is a service that sends requests to it. So you can think of it as like, if you have, say, an Nginx proxy, and then you have like another server, that's actually serving requests, something like let's make it very simple. Like let's think about a LAMP stack, like a PHP process that's, just running through requests. And if you don't have that kind of feedback mechanism between the PHP process and your Nginx proxy, that tells the proxy that, hey, I'm just overloaded. I'm doing too much work right now. Please don't send me requests anymore. Or, I'm up, but, I'm still not healthy. If you don't have that feedback loop and these kind of, ways to tell, your upstream that you should not be sending requests to me, then that's when a lot of these problems arise. So one of the ways to address this would be just to have better back pressure mechanisms. And back pressure is a topic that, it just crops up everywhere. TCP, for instance, let's start with something that's very fundamental to, a lot of systems we build. The very lowest layer, we have something like, TCP/IP, and these protocols have back pressure built into them, right? We have ways where, we can literally say, well, don't stop it sending me any packets. So a lot of these techniques are built at the very lowest level, but a lot of these techniques, what I've seen is that in real world systems, at higher levels of the system, these mechanisms just don't exist. So a good example would be, just what I mentioned, you have like a proxy sending request to a service, and the service is obviously struggling. It's not completely down, but, maybe a database that it's talking to is very slow. So, even if it's not completely down, a lot of the responses are very, very slow. And, in that scenario, just sending this process more requests is not going to make it any better. In fact, it's going to just increase the load on the database, right? So just having that kind of back pressure mechanism where this process can, tell the proxy, don't send me any more requests, I'm obviously not very healthy, but I'm also not completely down. I think that is one way to address this. Another common failure mode is with queues, where people just think that with asynchronous communication, you can just throw any amount of messages into a queue, and it's just going to churn through all those messages, and at some point it's going to complete them. But one of the most common failure modes of queues is, again, the lack of back pressure when the queue cannot tell the service that's sending it requests, hey, stop, don't send me any more requests. So one of the most effective ways to sort of deal with this problem is to just apply, better back pressure, and to actually tie that to the health check status. So, when you're actually health checking a system, the system can actually say, hey, I'm not completely healthy. And this is one form of back pressure mechanism. There are a bunch of others. This is like one of the most fundamental forms of applying back pressure by saying, hey, no, I'm not accepting the request because I'm not healthy. And certain proxies already come with inbuilt behavior, or they come with features that enable this. One good example would be HA proxy. It has this notion of general health checks, but it also has this other notion of health checks where a system can basically tell the proxy that I'm not completely healthy. You have the same notion built into systems like Kubernetes, where you have liveness checks, right? You have readiness checks and liveness checks. The two kinds of health checks in Kubernetes. And one of the checks is basically to say, hey, I'm up. The other one is to say I'm ready to start taking traffic. So a lot of these techniques have sort of been built into certain systems, but I don't see it built across the board in all kinds of systems. So if you're relying on a system that doesn't have better back pressure abilities, or better ways where a service can apply back pressure, then a lot of that needs to be built into the service layer. Thankfully, some of this was, I don't know if this is a good or bad thing, but they're just different protocols, different applications, just different layers. And in general, there are ways of applying back pressure at multiple layers. And knowing when and where to apply it is more a matter of systems architecture. I cannot just say if there's just one true way of doing it. Sometimes it comes at the protocol level, sometimes it comes at the proxy level, sometimes it comes at a certain higher or lower level. So, but yeah, effective back pressure is one of the proven ways to fix this problem where a system can get completely overloaded. There are also a couple other techniques that can be used. One is just, when load testing a system before it goes live, one thing that we could do is just have better models to understand the system's characteristics. And a lot of this is, prior art from fields of branches of engineering, like control theory, or even queuing theory. So when talking about control theory, we're talking about, we have like notions like the PID loops, which is so a PID loop stands for like it's a concept that comes from control theory, and PID stands for proportional, integral, and derivative components. So the idea is that if you build a system which has all of these three components, then you just establish better feedback loops, and that should help a system deal better with a lot of these transient failure modes. For people who want to learn a little bit more about PID loops, you could either get started with control theory and learn a little bit more about that, or there are also a lot of good talks on this topic. I know you work at AWS, and I know AWS has invested a lot in the control loops and control theory, and there definitely are a lot of great talks on this topic by people who have way more experience with this branch of engineering than I do. And the other one is also queuing theory, which sort of like helps one model systems as either open systems or closed systems. And again, I'm not an expert in queuing theory, but there are very good talks and very good resources for people who want to learn, how queuing theory can help model how saturated or how much load a system can take, and then do capacity planning based on that.
Yeah, So quite interesting. I learned PID loops back in computer science. I don't know how many years already. Probably 20. And it's not something new. And every time when I
Yeah.
speak with people about this technique, people just looking on me like I'm inventing
Yeah.
something. Do you think why? Why it's happened? Just hit me. Why it's happened like this? Why people consistently do not know about techniques which was invented in 1980 or something and do not apply them? How do you think? Because I see a lot of time people misuse queues, do not have, not even back pressure, don't have any feedback loop on what is going on in the system, and do not even put it into the system. So like, why?
I would say one of the so I'll be very honest. I only learned about PID loops maybe like 3 years ago. I didn't know much about this before then, and so when I go back and think about why didn't I know it before then, one of the examples or one of the reasons is that it's not something that's very widely talked about, and people learn things when you have other companies who've had a lot of success with these techniques who come out and say that hey, this is what we do and this is what's successful for us and this is how it works, or we feature a lot of these techniques in talks like these or in conferences like these where people can actually get to learn some of these things. I mean, that's how I learned about it. When I watched a bunch of conference talks and I was like, oh, this is very interesting, I've never seen it from this way, and then you kind of start digging more into it and you're like, oh, this completely makes sense. So I would just say it's more a awareness problem, and I guess one way to raise awareness would be to just talk more about it and just possibly write more articles about it and just explain about people's experiences about how these things work.
One thing we did not mention that you have a great Twitter and you have a great blog on Medium with a bunch of articles. So if you want to learn more, go for Copy Construct and you will find out a bunch of information regarding this stuff. Hey, we talked a bit about graceful degradation techniques, and I'm quite curious. What's your perspective? Hey, we have some technique, but technique is already quite complex for distributed system. How we can ensure that this technique is actually working? So how we can prove for ourselves and for our customers, probably if they're very curious about it, that technique is actually doing what it's have to do. Because one thing is just to implement it.
Mhm. you know in my experience, this is a little cynical. People truly understand why something is needed only when they've sort of been burnt by the lack of it. So I learned a lot about these things because I was working on teams on large scale systems where we had outages because a lot of these techniques were not implemented because we just didn't have back pressure, right? We had like 5-6 hour downtimes in some cases. We have customers who are angry, and when this happens, you're like, oh, okay, this is important. So I call that trial by fire because you just have to kind of you just have to learn it. There's no other way. You make mistakes and then you get burnt and then you come out wiser. So so that's definitely one completely foolproof way to convince people that they need back pressure, or they need any of these different distributed systems techniques, or concepts that they need to implement, is because when they don't have it, their system falls over. And I think it would also be in some cases, I also think that there is some value in letting people learn it the hard way, because a lot of talk about distributed systems and a lot of the literature that comes out on distributed systems either comes from academia or it comes from very large scale companies like Google or Amazon or Facebook, who publish papers on how they build systems. And this is good and this is very educational, but we live in an era where everyone is building distributed systems, and not everyone is building, the largest scale system in the world. So a lot of the techniques that, trickle down from like an Amazon or a Google is not necessarily what most people need. So I also think that, there is some value in saying that, let's start with something simple and then we get burned and then we implement a lot of these techniques because, in my experience, no company has gone completely bankrupt, at least in my living memory. No company or no startup has gone completely bankrupt because they had a single outage, right? A lot of the times, a lot of the very high growing startups, especially here in the Bay Area, they start with a very good product and with, somewhat meh infrastructure, and then they have problems, and then they actually scale up the infrastructure. They re-architect their systems, or they add better features, or they just move to a different stack, or they do something in order to scale. And that is a completely valid approach to thinking about systems, because not everyone is building like Google-like systems on day one, so you don't have to necessarily apply all of these techniques. But there usually comes a point, and you don't even have to be Google scale, to be honest. There comes a point when you're like much smaller scale, where distributed systems problems start to bite you. And that is when people actually really start taking notice. But, I would just say for a lot of people, it's totally fine to start, basic. And a lot of people don't like this, but I think it works pretty well. And, in my experience, for a lot of companies, it has worked pretty well. The other way to, I guess, convince people that this is necessary would be to basically, just show the evidence, to basically just show the proof. And, one of the ways where, and I guess this is one of the reasons why something like observability is so important, because if you don't really know what's happening with your system, if you don't really understand the different internal states of your system and how that impacts something like latency and response times and the quality of service, then it's very hard to even begin to understand where a lot of these problems come up. So and observability is sort of the answer to this question of like, how do we convince people? Because, you show them a graph, you just basically show them, real data, show them a heat map saying that, here's how this looks, here's where, here's when we started applying all these back pressure techniques, and look how the response time went down. This used to be like a P99 response time, and now it's, dropped to this. And, there's a saying in English that proof is in the pudding. And the answer is that, you just show people evidence, and most people in tech are fairly scientific, and people will just understand it. So yeah, that would be my answer.
All right, yeah, that's quite interesting. Then let's talk a bit observability because observability currently is new black, I would say, and everyone starts speaking about observability. I have doubted that everyone understands what they're talking about, especially. Yeah. So, when you say observability, what exactly you mean under it, and what kind of things you're looking for when you say no, system should be observable?
Mm-hmm. One of the key aspects of observability is, can you understand what's happening inside your system? Like, the various states of your system. One good example would be, we started this binary entity in that, there are many different levels of healthiness, so as to speak. And, to truly understand this, the spectrum of states, the spectrum of health states through which a system could transition, you really have to be able to see what's happening. And observability is just all about, can you understand what's really happening with the system just based on external data that the system is emitting, right? In this case, we're thinking about, can you completely understand the full spectrum of health of a system just based on certain signals? And I would say that is mostly what observability is all about. Whereas monitoring, which observability often gets compared to, is, it comes down to this world where, health is a binary thing. Like, can you monitor your system? Is it up or down, right? Those are the only kind of two things you can monitor for. And that's typically what people do monitor for when they monitor applications is, just, well, is it up or is it down? And then they make decisions based on that. Whereas observability is kind of like understanding, what are all the various different states of this machine? Is it something like, 60% overloaded, which means that, yeah, in theory, it's healthy, it's up, which is what monitoring would detect. But it's probably in a state where it's kind of somewhat unhealthy, it's a little overloaded. it could potentially fall over if you're going to send more load to the system. And, that's a very tactical way to think about observability is, can you really understand all of the different internal states of a system and just the various ways in which systems behave and the various emerging properties of distributed systems just based on data that the system transmits, or just based on data that the system emits, without having to go and SSH into a box and somehow prod what the system is doing, or somehow actually poke at the system to see what it's doing. So just based on like data it emits, can you understand what the system is really doing and in what state it's operating? So I would say that is the primary sort of like thrust behind wanting to differentiate monitoring and observability. And I think they both have their place. Observability becomes increasingly important as we run large scale systems because, as we've just been talking all this while, it becomes very difficult to understand distributed systems failure modes, or to kind of like even understand what is really an optimal or a healthy state for a system. Whereas with monitoring, we're mostly thinking about, is the system up or is it down, right? Do we need to scale up or not? So a lot of these decisions are, fairly orthogonal. And I would say monitoring and observability are actually fairly orthogonal. One doesn't replace the other. You kind of need both. You need monitoring because you need that sort of like very high level metrics. You need to know if your system is up or is it, if it's down. And you need observability to sort of like build a lot of these advanced capabilities which help systems to kind of stay up even if they're somewhat unhealthy, if that makes sense.
Yeah, keeping system up while it's unhealthy, it's probably the best scenario. I remember one of talks last year, actually on another conference, engineer from Netflix who give a talk, say, you know what, like, I give a talk here right now, but by the way, I'm on call at the same time, and I'm almost fine with it. And engineer was responsible for CDN of Netflix delivery infrastructure, which is mean like if something going wrong, nobody can watch a video. And he said, system every time something going wrong, and system itself trying to figure out how to fix it, based on data which we submit from nodes, and selecting in another route, so selecting another control loops. And that's kind of piece of art which I like. Do you have a similar experience in your career? One system just self-healing?
Yes, I would definitely say yes, because that is the ultimate goal with building large scale systems, right? In that you want as minimal human interaction with the system as possible. You don't really want operators dealing with a lot of system failures. And if you actually look at the evolution of like distributed systems, this has always been the main thrust, right? One of the main reasons why cluster schedulers are a thing is because no one wants to be provisioning machines. No one wants to be literally updating load balancer configs when a system is down, but you kind of like want all of this automated. It's almost like taking a lot of manual processes which require human intervention and building systems that can sort of do that. So obviously Netflix have done some really good work with the CDN and Open Connect networks. Another good example of a company that actually really incorporates observability data into their systems is Facebook. I'm not saying Facebook alone does this, but they've definitely published a lot of research on how they do it. So if people are interested, they can basically go read up some of the white papers from Facebook, especially a lot of the papers on their traffic engineering architecture. So I'm just thinking about papers like Kraken, papers like Maelstrom, and sort of systems like Proxygen. These are like very Facebook specific systems. Just disclaimer, I have never worked at Facebook myself. A lot of this is just talking to friends who work there and reading a lot of the research that they put out. And if people were to go and read about these systems, they will realize that a lot of the observability data that Facebook systems generates are not just used for like an operator to go look at a dashboard and see what it's doing, but a lot of this observability data actively feeds into other systems. So a really good paper to discuss here would be Maelstrom, which Facebook published about a year or two ago. and I think it was about a year ago. And it's basically how they do large-scale disaster recovery tests. So, if a data center were to go down, how do they live redirect all traffic from one data center to another? And a lot of this is done at the load balancer level, where they drain traffic from like services, even stateful services, and then start redirecting a lot of the traffic to other data centers or even other regions or countries. And the way a lot of this is done is based on telemetry data. It's based on fine-grained observability data that feeds into their monitoring systems. And a lot of the tooling and a lot of the systems that actually do this traffic draining read that telemetry data and then use that to, implement draining of traffic, or implement like shifting of user traffic or user connections. So, in more advanced systems, observability is used not just to understand the system, but also to build other systems which can use this data and automate, potentially very complex tasks. So, that would be an example of, using observability data, not just to understand the system, but also to basically build other systems around it.
So we basically have a pipeline. We have production system which emits some data, and we have kind of control system which correct production system if something get different. So basically exactly the same PID loop. You have your system,
Yep.
you have regulator,
Pretty much.
you have back loop. Simple.
Yeah, pretty much.
Nothing changed in this planet for a while.
Yeah.
Okay.
Yeah, people
it's
on
interesting.
Facebook don't publicly call it PID loops, but that's kind of what it is, right? That's kind of what a lot of these systems are. So yeah.
Yeah, while you speak, I open a link for PID controller, and I open Mainstream link and say, oh yeah, it's
Yeah.
exactly the same. Quite
Yeah,
interesting.
pretty much.
Probably another question which I would ask from people who building system, at what point in time you said we starting small, we're starting with something which is probably just working. What point in time or what signals you need to look for to say, okay, it's time to start building PID loop and start to building second system which will control what we're doing before it's get to real disaster? Yeah.
Usually, I think people. So in my experience, systems don't just completely just blindly start falling over one day, right? Unless you're like, you just get this viral amount of traffic overnight. You're a small little application that no one hears of, and then suddenly you're like the top 10, apps in the app store or something. And in that case, it's possible that the backend can crumble over in a day. But in my experience, what I've seen is that a lot of systems, and this is generally true for distributed systems, for all kinds of distributed systems, and that they evolve. They, when I was working on a previous company, we kind of started off, with very, very few customers and with, not that much traffic. And then for us to sort of like hit the point where we're doing like 1 billion requests a day, then we did 3, then we did 5, then we did 10. There's this sort of like exponential growth, as it is with the case of a lot of good startups, but it didn't again happen overnight. It sort of usually happens in a way where we can sort of like, we get some amount of time, we can sort of like predict what's going to happen. In our case, this happened over something like 3 to 4 years. So, the one good thing is that in my experience, companies don't go from like zero to like, overnight doing 5 billion requests a day, in one fell swoop. Usually it happens like over a period of time. And, so I would just say, just let your own growth and let your own traffic patterns and, let your own usage dictate how the system needs to evolve. Because, for a lot of systems, they don't really need very ultra sophisticated systems, right? In a lot of cases, like we talk about PID loops and other things, but, we can also build systems that are very, very simple where, they just crash, and something comes and restarts them, and that's fine because, that meets the level of SLA needed for that service. So I would just say that, in my experience, and I can only talk from my experience, usually, just growth and changing traffic patterns and changing usage have been good indicators of how the system design needs to change and evolve. I haven't worked on a service that just went from like 0 to like, doing Google level traffic overnight. So, obviously maybe there's systems inside Google that do that, but I haven't worked on those kind of systems. In my experience, a lot of the scaling up has sort of been gradual. So that sort of helps people. It sort of gives time for engineers to kind of like understand how systems evolve. But there are also different kinds of systems. Like if a very large company is launching a very new feature, and they're just doing a big launch to the world, then it's very possible that they're just going to get like a barrage of signups overnight, and that could basically take their system down. And in these kind of scenarios, it helps to forecast the load. A lot of people do something called load testing, which is in the most basic of senses, you just have like a load generator, something like a AB Apache Bench that's just generating a number of requests, and that's you just try setting a system something like 1,000 requests, or setting a single process 1,000 requests, or maybe like a whole system something like 1,000,000 requests, and see what happens. And that sort of works, but there are also possibilities that that is a little too primitive for systems that just end up getting like way more load than people expect. And in my experience, systems tend to fall over when people don't account for the amount of traffic that they're getting accurately. And in my case, working at companies where we try to onboard customers who send us a tidal wave of traffic, and that's caused our systems to fall over, a lot of that has happened primarily due to misforecasting just how much traffic we're going to be getting. And that's just been my experience. Obviously there are like various, if you talk to different people, they'll have like different stories to tell. But I think one good way to get around this problem would be to just be able to do better capacity planning. And that brings us back to ideas like queuing theory, as opposed to just trying to run a load generator against a service, or just trying to just scale up horizontally or something. There are just more smarter ways to anticipate how much load a system is going to be seeing and plan accordingly. But but this is the sort of advice I'd give to people who are not working on the largest scale systems in the world, but are still working with distributed systems problems, but they're somewhat small to mid scale. And for people who do work with some of the largest scale services in the world, something like you can think about something like Twitter.com, right? What kind of load testing does Twitter do before they have like the football finals, or before they have like before election night, because that is when a lot of tweets get generated. That's when the possibility the system could go down. And this brings us to the notion of how do we better do load testing, but in a very realistic way, rather than just having like a benchmarking tool send a number of requests. And the way a lot of these companies do this kind of testing is by literally maybe increasing the capacity and shadowing some of the requests. So on a normal day, let's say that a service gets 1 million requests a day, right? And if they want to scale up to like 2x that amount, or if they want to see what it's going to look like to scale up to 2x that amount, one realistic way of generating this load is basically to capture all the traffic that the service is getting, which is like 1 million requests, and then sort of doubling that and trying to replay that traffic against the same service, but at 2x the speed. So that is one good way of sort of like understanding how the system might cope when it's like handling 2x the load. And this sort of brings us a little bit into the, I would say, what I call the testing in production world, where you sort of like testing a system with real production load, as opposed to like synthetic load. Not that synthetic load is completely useless. There are like a bunch of benefits to just running synthetic load against a service, but it's also much more valuable in many cases to just run realistic load against a service. So capturing all your traffic and replaying it at a different speed is like one way to sort of achieve that.
And we get to my next favorite topic, actually testing system in production. You mentioned one good reason why we can want to do it. Do you have another good reasons why you want to actually test your system, distributed system in production, instead of building like how it was called? Basically, was quote unquote best practice. That's your staging should be similar to your production. And I every time
You know,
laugh at it. Yeah.
well, first of all, it just takes an enormous amount of effort to maintain a staging environment that is completely identical to production, right? You could possibly set up like a similar stack. You can have like, a system that talks to, a database that talks to maybe, maybe there's some cache in between there. You can sort of set that up. And there's definitely some value in that. I wouldn't say that it's completely useless because, there are a lot of errors that you can sort of uncover by just running, you're putting your system through like other real systems as opposed to like complete mocked services, which is kind of what happens in a lot of unit tests. So I would say there's some value in staging, but I would, it's just not enough in a lot of cases to invest in a very sort of like complex staging environment which absolutely mirrors production, because first of all, it's almost going to be impossible to mirror production, because you're almost going to like, it's almost like you're going to have 2x the amount of servers that you're running, and to completely replicate production, you just have to run a parallel stack that's entirely like production, that's just for testing. And a lot of people don't do it because it's just wasteful, right? It's expensive to run that many servers just because you want to test. And even then, there are just a lot of issues which cannot be uncovered in a staging environment, right? Because, let's take an example where you have a system that talks to a database, and it's set up exactly with the same configuration as the production stack. But it's possible that the staging environment probably gets like 1/100th or maybe like a millionth of the traffic the production environment is getting. So a lot of the problems that only arise at very high levels of concurrency or very high load, just you cannot catch a lot of these issues in staging. So there's just a large class of distributed systems problems that simply only occur when you have the right sort of like mix of usage, concurrency, load, traffic patterns, and a lot of these things. And staging environments are almost completely useless when it comes to surfacing a lot of these problems. So so instead of investing a lot of energy and time into staging environments, it becomes a lot more valuable to sort of make the production environment such that it's more easier to test in that environment. So to make it very clear, testing in production does not mean that you just roll out your change and you let your users be your testers, and if you hit a number of issues, then basically users are hitting those issues, because that is what typically testing in production has meant. But when I talk about testing in production, what I really mean is building systems and building architectures so that it is possible to safely and securely test systems in production while not either ideally about completely minimizing user impact, or in the worst case scenario, making sure that only very, very small number of users are impacted, and you don't have a fully blown outage. So and if you actually think about it, here's what I find very surprising when I talk to people about testing in production, in that people either think it's very lazy, or people think that it's irresponsible, or people think that it's just wrong to do that. And what I don't see people talking about a lot is that to be able to safely and securely test in production, you need to actually architect your systems so that they can be tested in that way. And if you break it down even further, a lot of the best practices for building these kind of systems that can be tested in production are also best practices that just make systems way more reliable, that just make it possible for systems to operate better. So which is kind of what surprises me, because no one talks about that. It's not like testing in production is something you do. It's more like you build systems that can be tested in production, because then when you do that, by default, you're building in better practices. That's always going to help you, because what is production if not users constantly testing what your your services and your systems? That's kind of what they're doing, right? People are constantly testing all of these systems, and testing in production is just a more deliberate and a smarter way to do that, and to build in patterns that ensure that if a test goes wrong, which is exactly what happens when a user hits an issue, right? They're basically testing your system, they're trying to do something, and it doesn't work for them, which means that something has gone wrong. So when you build systems that can be tested in production, what you're trying to do is that, when something goes wrong, you're building in guardrails and you're building in mechanisms that would either minimize the user impact, or it would completely shield the user from whatever went wrong, or it would just make your system behave better in face of that very specific failure mode. Because something goes wrong is just basically a different failure mode that you didn't think about when you're building the system, right? And being able to test better and more deliberately in production would just mean that a lot of the failure modes can be better accounted for, can be actually architected around, and people will just have a better experience. So that is what testing in production actually is about. It's more about systems architecture, and it's more about how do we sort of make sure that the user has a better experience. It's not about, let's just make the users have the worst experience by just subjecting them to like a very buggy software. That is not what it is. It's more about, well, how is the user going to be better protected against misbehaving software or misbehaving systems?
Yeah, and I also heard a lot of opinions that no, you should not test anything on production. It's completely irresponsible, because like how you can do it, it's holy grail, but like where you will get data, and more for me it's interesting challenge every time. You have, as you said, you have failure mode for a system, and you need to check it somewhere. And for me, like production, it's only way to check it, because you have your real life environment around it. Otherwise, you need to replicate, basically make whole copy of a word. And people say, you know what, like it's not possible, so we'll just do nothing. And that's for me more irresponsible rather than just running the test in prod. But from this perspective, and I completely agree with you on architecture and the stuff. What's the most useful tricks you saw in the past, or maybe like what you want to use to have more testability for system in production? Obviously, we have observability pieces, but is something else?
Yes, I would say there are definitely there are multiple things that one needs to think about here, but I would say there are just two very, very important things, right? One is, how do you minimize the blast radius? And this comes down to sort of accepting the reality that, systems do fail at all times. And, irrespective of like, your best intentions, irrespective of like, implementing all of these really complex, distributed systems techniques, systems can and will still fail. So the first approach is, well, okay, we know that the system is going to fail. How will we minimize that failure? How will we minimize that blast radius? How will we make sure that if something goes wrong, only a very small number of users are going to be affected? And, that is the first thing, which is like, how do we reduce the blast radius? And the second more important issue here is, well, what happens to state? And, this is, again, something that I don't hear a lot of people talk about. What happens to, if you're testing in production, you're running stateful systems, right? What happens to, state that gets corrupted? What happens to state that gets deleted? What happens to things like, maybe you're running a cache and, there's some bug with this new code that you just released, which, causes some kind of cache poisoning, right? That can literally take down the whole production systems, because for a lot of systems, caching is just not an optimization. It is like a core part of their system operating in a certain way, and that if the cache goes down, the whole system goes down, right? So I don't really think a lot of people actually talk about these things. What happens to things like, personally identifiable information, PII, as we call it here in the United States? What happens to, especially for like a lot of healthcare software and other software like that here in the US, it's not complete. It's completely unacceptable for like user data to be leaked, or for, user data to somehow be corrupted in some ways. And, so these are actually very, very important problems to think about when you talk about testing in production, because, you have to safeguard your systems, and basically you have to safeguard your business against things going wrong, because that can open yourself up to lawsuits. So, testing in production is not without its, its challenges. And, so obviously the question, so now that we've identified these two challenges, the next question is, okay, how are we going to address them, right? So let's first talk about blast radius. So, one of the most effective ways to sort of like minimize the blast radius of a change gone wrong is basically to invest in better, staged deployment practices. Because, a lot of people still, when they deploy software, they basically do a deployment and boom, suddenly, 100% of the users are, talking to the new service, right? And that is a problem because if there's something wrong, then 100% of the users are being affected by that problem. So one of the most effective techniques to reduce the blast radius would just be to have a very progressive and staged rollout plan for the change, which is actually a form of testing in production because you're testing the change against something like, say, 1% of the users, right? And if there's some really big bug, then you're going to know right away in which you can roll back. And 99% of the users have not been affected. And the good news is that a lot of open source systems these days, systems like Spinnaker, are sort of built with a lot of these practices in mind. So it's possible to canary requests and, just slowly do a gradual release as opposed to completely 100% exposing all users to the new traffic. So, safe and staged rollouts would be the number one most important thing that people could do to, just better curtail the impact of, something gone wrong. The second most important thing that people could do would be to invest in safe rollbacks. Because rollbacks are actually a pretty complicated problem if you think about it, right? For stateless services, it's somewhat easy. You push out a change, something breaks, you can kind of roll back and things are back to normal. But for stateful services, the services that carry a lot of state, this can become problematic because, they can go and corrupt the state of some other service they talk to. They can go and corrupt the state in the database, right? And even if this affects 1% of your users, that becomes unacceptable because, that is just not allowed. So, in a lot of cases, it's legally not allowed. You cannot do that. So, so it definitely, after investing, in having a very good deployment pipeline, we can safely roll out changes. The next thing to worry about would be, well, how do we roll back changes if anything goes wrong? How do we sort of like unset what went wrong? And again, there are just different ways of doing this. One would be to purely, as you do the staged rollout, make sure that, the first 1% or the first 2% or the first 5% of people who are actually being, redirected to this new service are actually like internal users or they're kind of like test users, right? So even if something goes wrong with the data, that's okay, because they've opted into that. So, that would be one way of doing it. A lot of companies also call this dog fooding, where they sort of like, if you're building a service and you rely on the service, then, when you're progressively deploying, you make sure that the first 1% or the first people to actually be exposed to the new service are like internal employees or, employees, at the company. So that also helps people just build better confidence. And this is also very true, at companies where one service is being used by other people at the company, right? Something like, I think Amazon would be a good example where, a lot of teams, from what I understand, depend on S3, but, all users also depend on S3. Like every AWS customer is using S3. So, if you want to like do a new deployment of S3, then, first expose the new change to just internal customers or, just even internal facing customers who are not dealing with user data. And then, build confidence in, the quality of that change, and then deploy the change over, to all users. So I think the next thing would be obviously to invest in better rollback practices. The third would be, these are more, we're still on the topic of blast radius, and we're just veering more into this territory of like, well, systems architectures, right? Like how do we build systems so that the blast radius is small? And another good technique would be just, better compartmentalization. So, when you're rolling out the change, make sure that you only roll out the change to like one region. Don't just completely roll out the change to like multiple different regions, right? And, if you're just exposing 1% of your users, make sure that all of those users are in North America, that, they're not just like a cross-section of users from across the world. And, so just having better compartmentalization and just better isolation between regions, between zones, and, even just between user traffic is like a good way to think about like, how do we minimize the impact of a change gone wrong from, affecting other people or, from affecting a larger cross-section of the user base. Other techniques are things like, well, how do we build highly reliable data planes, or how do we build highly reliable control planes? Because, we talked about this a little earlier, where a control plane is like everything that really controls a system, right? Everything that, maybe consumes like things like observability data from a system and decides how that system needs to be configured, or how that system needs to change. And a data plane is basically like the part of the system that actually serves user traffic. So all the user requests flow through the data plane. It's in the path of every user traffic, whereas the control plane is more of a component that sort of like configures the data plane, or it basically understands how the data plane needs to work. So, and if you actually think about it, the best practices for building control planes or data planes are not the same. They're actually fairly different, right? And I don't know how much time I have here to go into a lot of those details, but I actually did write a blog post last year in, which details the best practices for building resilient control planes and data planes and how they differ and how we can build better control in data planes that actually help you to test more of your system in production. So, so obviously reducing your blast radius. And there are multiple other techniques as well. I don't think I have time here to discuss most of them, but that becomes the number one most important thing that people need to think about when they talk about testing in production. And the good thing is that these are things that people need to be thinking about anyway. It's not something you do just because you decide, oh, well, I want to test in production, so let me go and implement all of this. These are things that people need to implement, if they're running a production system which has a lot of users, because, things going wrong can impact your users. So when you build in a lot of these techniques and, you're just building better systems, you're building more reliable systems, and you're building systems that can help users. It's just going to improve the user experience. So, that's kind of why I say that, testing in production is not this scary, irresponsible thing, but it's actually something that's really difficult and requires a lot of effort and a lot of thought and, a lot of engineering effort, to be honest, because, to be able to safely test in production, you have to implement a number of other additional things that you need. And the good thing is that when you implement a lot of that, it's just going to make your systems more reliable. So, it's testing in production is not something that you just go and do and, as if it has like no other impact on anything else. It's, it's just feeds into like, the betterment of the system as a whole. So, that was, the topic on blast radius. And the next question is obviously how to deal with state, right? And this is really problematic because you obviously do not want to expose users to, corrupted data, right? Even if it's 1% of the users, they really don't want to be dealing with a lot of, bad data. Or, in some cases, like a state change can completely take down the system. And these are more scary because, what happens if you're trying to change this, if you're trying to like test something like an edge load balancer in production. An edge load balancer is like the very first thing that's going to be running inside the infrastructure that a user traffic is going to interact with. In a lot of cases, all that an edge load balancer does is something like terminate TLS, right? But if there's a bug with the software, and or even worse, a bug with the configuration of this proxy, that's going to like suddenly impact all of the requests that are touching that system, right? So and if there are bugs with something like TLS termination, then that can potentially leak user data. So the problems here is that state is a much harder thing to deal with, and you have like again state at like multiple different levels of the architecture. The state at the edge, there's state within like what I call like the intra-service state, which is like if a user request is going to traverse through like 3 services before it actually hits the final service that's actually going to process that request, then there's a possibility of state corruption at all of these intermediate services. And this is a hard problem, and when you're testing in production, if you cannot get it wrong. But the corollary is that if you're scared that you don't want to test in production because you could get it wrong and that could lead to big problems, then it just means that if there is a bug that slips into production, it's going to cause the same problems anyway, right? So it's not like testing in production is going to make it any more riskier that you're going to like corrupt user data, because if that bug slips into production, that can cause corruption to user data at a much larger scale. So again, there are like a whole bunch of like different techniques to just better build stateful systems that can be tested in production, and where we can either completely minimize or in some cases, you can even completely eliminate like data corruption or any kinds of like data loss or any kind of like corruption to state. And a lot of this is the content of another blog post that I'm actually authoring. I don't know how much time I'm going to have today to go into a lot of these techniques, But it's going to be the topic of another blog post that I'm writing, and when it's done, all of the information will be there. So so blast radius and state are like two of the hardest parts of testing in production, but those are also two of the hardest parts about distributed systems in general. It's not just about testing in production. It's all problems that are like testing in production problems are just distributed systems problems. You're just making it easy because when you build systems that can be tested in production, all you're doing is that you're just making it easier to surface and understand these problems before they impact users. So these are not just testing in production problems, these are distributed systems problems.
Wow, it's a very interesting way to look on it. It's reality. I never thought about it. That's just another distributed system problem. Speaking about of time, we have 10 more minutes to go here, and then we'll have discussion room when we can have a chat. And for last 10 minutes, I would like to ask you about your forward-looking vision for distributed system. So what will be the next topic, let's say, in next 3 years, next 5 years? So what your thought on it in distributed system computing?
Well, I would say that there are just two sort of like different areas where I think we still need to make a lot of progress. One is more an active research area, and it will be very interesting to see how a lot of these techniques can sort of like trickle down to like real world distributed systems. It's already started to happen at some of the larger companies which are actually doing a lot of these research, but it'll be very interesting to see how this can be democratized, and the entire distributed systems community can gain from a lot of these research. And I'm talking about research in like the ML AI area, because we're seeing a lot of really interesting research on how to apply better ML techniques to like distributed systems problems. So, one of the researchers who's doing really, really good work in this area is, I think he's called Tim. He's someone from MIT. I forget his name, but a lot of the work that he's done is like how to apply techniques like machine learning to problems like building databases, right? How do we build smarter indexes with learned data? How can you sort of like understand the traffic patterns of a database to kind of like just use better indexing, or completely do away with indexing, right? So a lot of this is very, very interesting research areas right now, and I will be very interested to see where this all this heads, like maybe in the next 3 or even 5 years. I mean, another good example of applying ML to like distributed systems problems would be how Google does autoscaling. So they published a paper, I think earlier this year, or maybe it was end of last year, where they talked about how they do autoscaling at Google. Because a lot of cases, autoscaling is a fairly sort of like manual process, in that you manually decide to autoscale, right? Or you somehow autoscale based on some kind of static threshold, based on like something like memory, the amount of memory used by a system, or the amount of like CPU being used by a system. If that gets over a certain threshold, you decide to sort of like, well, you need to scale up, right? And a lot of this has been good, but there are also a lot of different problems with very, very static thresholds. And there's definitely a lot of research that's coming out which sort of use machine learning techniques on like live traffic, right? The live traffic that a system is seeing, to kind of understand how to better autoscale. So and there are a whole bunch of other examples as well. So I would say these are two these are two good examples, but in general, this is like a very good area of research. And I would be just very interested to see, where all this heads, maybe like in 3 or even in 5 years, where, if we can build better distributed system algorithms, not systems itself, but like a lot of the algorithms at the heart of a lot of these systems that, can just learn based on like the real traffic it's serving, as opposed to, static thresholds that an operator might set. So that is like one really interesting area of research. On the other end of the spectrum, something that I think would be really interesting to see, or something where I genuinely feel that the distributed systems community should be going, is to sort of make, or to sort of like build better abstractions around distributed systems, where it becomes a lot easier and a lot more approachable and accessible for a lot more people to be building systems, but without necessarily sort of like, understanding the guts of how to build systems. A good example in my mind would be, something like Kubernetes is kind of the standard for cluster orchestration these days. Whereas, I see Kubernetes as more of a very low level tool. And, what it's really missing is like just better higher level abstractions that make it really easy for someone to, just deploy a new application, or, just to basically like bootstrap something new, but without having to understand like, all of the different Kubernetes concepts, right? Or even like concepts about like what is a pod, and like, what is like a service, what is the deployment, like what is, without having to understand any of that, if people can just like deploy their applications using some like very easy and intuitive APIs, but without really have to understand the guts of like what's underneath that. So, I think that is something that is actually very, very direly needed. And, as I tell my friends, it's kind of really sad that, in 2010, we had something like Heroku, which was, for those who are unfamiliar with Heroku, it is it's kind of like a platform as a service, which makes it really, really easy to deploy applications. You literally deploy with Git. So it's really that simple. And, Heroku just makes it really, really easy for anyone to spin up new applications. And we kind of started with that 2007, 2008. And then, in 2020, we ended up with something like, Kubernetes being, the state of the art, which is, it's good because it definitely has solved a lot of very complex distributed systems problems. But I also don't think that a lot of engineers who are building systems, who are running services, need to understand something that complex. They just need better, higher level APIs, but make it as easy to use as Heroku. But, you get all the benefits of, everything that it does underneath the hood. So I think that would be the second area where I want to see a lot of the distributed systems, like real world distributed systems research sort of like play out, where, you just have better, higher level abstractions. And this is actually true for like everything. It's not just for Kubernetes. We need good higher level abstractions for deployments. We need good higher level abstractions for like understanding what systems are doing, right? We talk about observability, and it is good that, we're able to emit all of the data, but, the reason why a lot of, in my opinion, the reason why a lot of observability systems that exist are sort of like, have a lot of shortcomings is because they don't make it easy for people to sort of understand. You're somehow dealing with very, very low level, like very fine grained low level data that a system is emitting, but you don't have these easy higher level abstractions like really good visualizations or the ability to correlate changes, or, the ability to correlate what's happening across different parts of a system. Like a lot of these abstractions don't exist. And that just makes a lot of these systems, a lot of these tools really hard to use. So same with, a lot of the things around, load balancing, a lot around RPCs. Again, I just kind of feel that for a lot of these very common everyday distributed systems problems, what we're really lacking is just higher level, easy to use APIs that make a lot of these more accessible to people and make it more transparent. So in some cases, and in other cases, what you really need is just better encapsulation. So yeah, I think that's kind of what's missing. And that's where I would like to see the industry head in the next 3 years.
Makes sense. So basically democratization and commoditization of distributed systems. So something similar happened in Java world back in the years with G2E, and when you just build your Java class, pull it somewhere, done. You have it working. It was amazing, and sounds like modern techniques going to the same way, just reinventing it for distributed capabilities. Oh yeah, it's cool. We have
that's kind of what happens. That's kind of what happens a lot of times, right? And that, what's like a lot of times we just go back to research that happened like back in the 1970s, or even with things like PID loops back like, 100 years ago, and we discover, oh, hey, here's this new way of solving this problem, and people have always done it in different contexts or like in different ecosystems for a long time. But yeah.
Well, yeah, PID loops, it's amazing. We have almost last minute, and I would like to say thank you for this great talk. I really enjoyed this time, and it's amazing. And if you can help me to summarize key takeaway after it would be great. So we speak about system health, and that's you definitely, it's a spectrum. not a binary stuff, and we spoke about a lot about testing in production, and that you need to actually prepare for it and put a lot of efforts to make system testable. It's not getting for free. Anything else you want to highlight for our audience?
Always, start small, and it's good to have a very good general knowledge of just what's happening in the world, but also it's important to just solve the actual problems you have at hand. And so always keep it simple as much as possible. Try to just solve the actual problem you're facing rather than just using some technique that Amazon or Google is using just because it sounds cool. And I would just say that just actually be focused on solving the real problems you have, and good luck.
Yeah. Plus one on this. This was already too complex, not overcomplicated. And yeah, you will need the luck for sure. And
All right. Thank you very much. Thank you, Michael, and thank you, Cindy, for for that interview. And I remind you that we have a Zoom webinar where you can follow and ask more questions if you want to. So see you there. Thank you very much.
yeah, thank
you.
you, Cindy. See you in the Zoom.
Bye.
Bye, everyone.